Hey everyone, good afternoon. Thanks for coming to my talk. I'm happy to be back at Kotlin Conf for a second year to talk about some exciting work that we're doing at Uber. For those of you who don't know me, I'm Ty Smith. I'm an engineer in our dev productivity org at Uber. So we typically work on supporting our internal developers. We work on the tools and libraries and frameworks to help all of those engineers be successful and deliver our apps internationally. I was getting ready today to give a talk about some of the migrations we're doing in AI, and then it was unfortunate because JetBrains just announced Junie for Android Studio, and I thought, well, maybe that can do all of this work, and we don't need to do this anyway, and we can all go home. But in case that doesn't work, maybe there's still some good content here for you. So let me give you a bit of a background, because this is important to where the project is going. I want to walk you through a bit of the Kotlin history at Uber, where we are now, and a little bit of how we got here, before we get into really the meat of this presentation. So we started with really early adoption, back around the time that Google announced Kotlin as a standard language for Android. We had some prior to that, but that really kick-started the community, and we worked on a lot of fundamentals that were needed to really scale that out over the following years. There were a lot of early challenges in the tooling maturity and the specific limitations that we wanted to adhere to. And so over time, we got to a place where we had kind of grinded through those, and we started to see major adoption amongst our engineers internally. We have hundreds of mobile engineers, and that became kind of the dominant language over time, to the point where we ended up joining the Kotlin Foundation. We banned new Java, and funded a fully staffed Kotlin platform team, and started doing central migrations. So it's been a long journey, but let me talk to you about a couple of the critical points. In the early years, there was a lot of friction that we experienced. Some of this was internal, like politics and things that you would experience at a big company, and some of these were technical friction. On the organizational friction, this might be familiar to some of you if you've done this at big companies as well, but there was a lot of management concern around a new language coming in. They had seen this happen with Swift a little bit earlier, and the teams adopt that a little earlier than they probably should have, around 2016, 2017. And there were a lot of challenges that really came out of that, and there was a lot of consideration if it was the right time that they should have done that. Similarly, the company had just gone through a big hyper-growth moment, and there was a huge amount of fragmentation, and they were trying to actively converge down on the back end. And so coming and saying, hey, C-levels, we want to add a new language when they're trying to converge, it came with a little bit of skepticism. Second, it would take a decent amount of headcount and prioritization to make this happen, not just in a small bit, but at scale. Uber works in monorepos, so it's not like one single app and one single repo could start adopting this. It really did need central funding, and that was competing against all of the other company priorities. Developer education was also a challenge. You had hundreds of Android engineers that we needed to help migrate from using Java as their dominant language to working on Kotlin over time, bringing in external resources, doing internal trainings. These were all challenges that we faced. And on the tech side, we also, again, we were in large monorepos, so we had really big scaling challenges and tooling requirements that at the time, Kotlin just didn't meet. We had to put a lot of work in to make that the case. We had to really mature and standardize linters and code formatters, and port over the language pattern linters that made sense from Java. There was just a lot of effort that was required. And at the time, the build times were also really challenging. In 2019, we worked with JetBrains and published a public study that analyzes the build performance in Kotlin in a number of different scenarios. We did this using generated code in our monorepos and came out with a lot of interesting data. We don't need to go through all of these, but at the top end, you could see a somewhat common use case can result in 5 times the standard speed of Java. And so, we were using error-prone, and we had APT and some other things, so it's not quite the 5x. It was more like a 2.5 to 3x for those use cases. But it really made us think about what constraints and what patterns we wanted to put in place as we started to allow developers to use this. Otherwise, they would really start to suffer from poor build times. But over time, we invested heavily, and we started to really see the developer community come around to using it. We measure NPS, the Net Promoter Score, and so twice a year we have our developers fill out a survey and rate their satisfaction and give us a ton of feedback. And we've seen that go up consistently as more Kotlin adopted over time, and we've invested in the surrounding tools. Other than that, we've done some studies and seen really key benefits to using Kotlin versus Java. We saw increased productivity, we've seen reduced lines of code, we've seen the cyclomatic complexity go down, the general satisfaction of the engineers using it is up, we've seen less null-related issues in production, and overall, runtime performance can go up as teams specifically target language features that make sense, like inlining or coroutines in certain use cases. And a couple years ago, we decided, as we were thinking about accelerating these migrations, to get together with a bunch of other big companies, and we created an industry working group where we could talk about Java to Kotlin migrations. If some of y'all were here last year, you might have seen a panel that we were on, and we gave a bit of a talk about this. But it really empowered us with the education and the momentum to really take it forward and think about how we wanted to, at scale, migrate so much Java to Kotlin. When we joined the foundation, shortly after that working group was established, this gave us an opportunity to connect deeply with JetBrains and a lot of other folks that were thinking about this space. We were able to give a very concrete feedback. And around that time, maybe a little bit before, Meta had released their AST tools, which was a sample project that they used as the basis for their own processors to do code generation from Java to Kotlin, and they've done some public talks on this and some public blogs as well. So we started building some tooling on top of that. First, this is the developer is using this themselves. We created a tool called Rektify. It's built on top of the previous tool I mentioned. It's built into the IDE. This allows a developer to initiate a migration, and it will incentivize that in their workflow. If they open a Java file, it will prompt them to migrate this to Kotlin. It will handle the type of PR that preserves the git commit history. It will run the processors around to get cleaner code that we'll talk about in a minute. This is sharing a lot of the tech that we saw from Meta, so there's some industry alignment here. And lastly, this, again, the developer's doing this themselves on their own code. What does this look like a little bit? Well, we run a set of pre-processors and post-processors around IntelliJ's own Java to Kotlin conversion. I'll get more into what those look like in a minute. But once we've outputted those, we also run the IntelliJ JDK post-processor that was added somewhat recently, as well as an extension hook into the IntelliJ pipeline. So the pre-processors and post-processors give us an AST transform, and the post-processors can give us some type awareness. So we have a lot of flexibility in what we want to do with those. But this is running in the developer's environment, so they will then manually verify once they've done this. If it looks good, they can put it up for the PR up for review, and at that point it can run on CI, they can get it to go green, and hopefully they can land the code and move on. Now, we talked about the processors that were mentioned. We have several of these at this point, but you could think of these as specific actions to address maybe a specific gap or something idiomatic that didn't happen in the Java to Kotlin conversion. On the preprocessors, we can more aggressively add nullable annotations. Our repos use non-null by default, and we found that by having very aggressive nullable annotations in the Java from the information we already have from things like error-prone, we can prime it before it goes into the converter a little more effectively. And then on the post-processor side, this is things like potentially fixing Mockito imports or changing it from Java to Kotlin, or fixing the Android text utils. There's a lot of these types of things that you run into where it's just not idiomatic Java once the conversion's done and you want to go and do the cleanup. And we can start to do these with these processors that we have been building out. And so when we looked at this, and mostly people using these assisted tools in their own environment, and what the migrations were looking like, the engineers were migrating some of their code, right? They wanted to do it. They didn't want to work in Java code anymore, so they were migrating their own features or their own apps. But we looked out and we projected and we said, that's going to be a really long time that we still have to deal with Java. And we started asking ourselves how we could accelerate this and get it to be done a lot faster while doing it safely, of course. And so we're going to take a bit of a pivot, and I'm going to talk a little bit about large-scale changes. If this is a preliminary for getting back into the Kotlin migrations we're talking about. But if you're not familiar with these, it's a term that originally, I believe, came out from Google back in the day, and they've published some information on this. But it's generally the idea that if you have a really large repo and you need to do a really large cross-cutting atomic commit or a migration or a dependency upgrade, those can be really challenging when you have a lot of people working in the repo and you need a lot of different reviewers and you're challenged with rebases and like all of the other shifting bits out from under you. And what that entire process can look like in a big company, how you manage that, how you get all of those reviewers to sign off, how you handle the rebases. This entire process can be extremely convoluted. And this is also the couple years of AI where we have all of this hype going on from public CEOs, and they're saying things like, a quarter of all new code at Google is generated by AI, or Amazon's making really large claims as well around what they're doing. And so we started really looking into this because our leadership, like a lot of companies, is looking how we can invest further in AI, and we were wanting to kind of apply it to this problem space. So when we started to click in, we noticed that a lot of them are claiming a lot of this stuff from their existing LSC processes that then they're adding AI on top of. They have very well-established infrastructure to handle these large code mods that they can democratize across their company. People can submit language dependency upgrades or different types of things that would be needed, and it's going to handle the reviews for many different PRs that are going out and get into the right review groups and do all of the other sorts of stuff that if you're doing it manually, especially in large monorepos, it can become extremely complex and hard to deal with. We don't need to necessarily go through all the points here, but what we started to design our thinking around is there's really 4 different categories that we wanted to think about in large-scale changes. There's the problem identification area, where you're looking for how you solve the specific migration. There's the code transformation area, where you're actually doing code mutations. Safety validation, where you're saying, hey, does this actually work? And the campaign management, where you're saying, if I have 1,000 PRs, how do I get these all reviewed in time? There's a lot of use cases for these in general, right? I mentioned language migrations and dependency updates already. There's all deprecations that need to be cleaned up, mass linter changes. Huge amount of benefits that companies see. Staying modern reduces your security risks. It improves overall quality. You can stay up to date with potentially performance benefits that are coming in from the libraries you're getting. You can potentially lower your cost if something's more efficient to run in your capacity or on CI. But there's a lot of different ways that these can manifest themselves. It can be one large atomic commit that you have to do across an entire repo. It could have static changes that are risky versus runtime changes that are risky. How do you do the proper verification? You could have per call site needs to do the migration versus being able to do it transparently out from under libraries. And you may have nested dependency hell, where you have to start updating one thing, and then the next library, and the next library, and the next library, until you can get the entire thread pulled. So there's a huge amount of challenges. The toil on developers is extremely high. We fund full-time people just doing upgrades almost year-round in all of our monorepos. Each one is pretty unique. You can't look at a migration and say, let's just apply exactly what worked before on this one, because you have to kind of think about it like a piece of art, like all the unique bits of it, and how do you de-risk the different parts. They typically require very deep platform engineers to handle this change across it. The tooling across our different platforms is very fragmented. What is done in Go is different than what's done in Android, is different than what's done in our backend JVM repo. Can produce a really high volume of pull requests, and then you get into issues like the team's not wanting to review these. Like if they have 100 PRs sitting in their queue, how can you reasonably expect them to get through all of these and apply a good quality lens to this? So we started a big cross organization project called Auto Migrate. We started this last year. This was really to take all of the fragmented, bespoke approaches to large-scale changes that we had been doing for many years before and say, if we want to take advantage of AI and we want to be able to see the same sort of wins that we're hearing from Google and Amazon and Meta, we need this underlying infrastructure, and we need the muscle to do this properly in a standard way. And so I mentioned the 4 categories, but I'll give a couple examples. In the problem identifier, You might ask questions like, do we need to migrate each file? Do we need to have the atomic commit? Can we migrate per module? How do we shard this properly? In the code transformer, it might be, what is the actual tool to do the work that we need? If it's in a Java repo or a Kotlin repo, it might be something like open rewrite. You might have just shell scripts that are doing it. People might do regex. If you're in Go, it might be something like Go patch. You might be using guitar. There's a huge amount of tools and a huge amount of fragmentation, and you're going to see it all over the place. The validation stage, how do you actually make sure that it worked properly? Did your CI pass? Is that enough signal that you can push this to production? Do you trust that signal alone? Do you have to have humans testing this out? What does that look like? And then again, with the campaign management, I'm going to keep coming back to this, but actually getting people to review a large amount of code is a really hard problem. We talk to a lot of our peer companies who are a little further ahead in some of this bits than us, and they say they get into this state where there are just teams who don't review things. There's just a huge backlog, and they just have migrations that never get finished because they can't get that done. And at all points of this, if there's failures, it takes you back earlier in the process. If people in the code review say, no, this is broken, you need to fix this, it pulls you back maybe into the problem identification or the code transformer stage so you can fix it. Similar in safety validation, if your CI is failing, again, you're trying to debug and fix that. So it's this very expensive iterative cycle. So let's dive into a couple of these categories for Kotlin. I'm going to skip for now the problem identification one. We'll come back to it a little bit, but I really want to get into some meat so you guys can understand the story clearly. So we're going to talk about the code transformer piece and what we're doing with the Kotlin migrations we were talking about. So let's go back and talk about the pipeline that we had put together for Rektify on top of the Kotlin AST tools. Just a refresher, this uses preprocessors and postprocessors, and we put in a Java file and out comes a Kotlin file. So going forward, just to simplify the diagrams, let's refer to that entire process as just Uber J to K, and then I'll use this in several upcoming diagrams. So let's take one of these workflows. We have an engineer who initiates a migration on a specific file or set of files, and what we've built is a standalone pipeline to handle these migrations. So we run build-kite. Build-kite then initiates and orchestrates a headless IntelliJ instance that has the Rektify tools installed with it. And then we orchestrate the IntelliJ instance with CI to do the specific migration. Then we run the CI tests on it, and if those pass, it goes to code review for the team to review the change that happened. And if that fails at several points, then it comes back to the engineer initiating the migration, and they start to debug and look at it. They start to spin the signal. They're looking at our pre and post processors and saying, hey, there's use cases where this didn't cover. We need to write another one. When we talked to Meta about their process where they're a little further ahead, they said they ended up with hundreds of these rules just to get idiomatic code on a single migration that didn't require humans to go in and manually edit. So we have a bit of room to go, and this process does give that signal to the engineer, and they can write it, but it's quite slow. But with this, if we continue to invest this way, we project that probably in about 4 years, we could get to the same spot that would have taken us over 8 if we were letting the organic migrations go on entirely. So quite fast, much more efficient than the previous one, but 4 years for this still sounds like a lot of time. And so we again thought, well, it's the time of AI. It's about to be taking all of our jobs apparently. So in the meantime, can we use it to go faster and help us get rid of this Java code just a little bit quicker? So we said, well, why can't we just ask ChatGPT, hey, migrate my entire repo to Kotlin? That should work, right? We looked at that, and there's some positives. It's very flexible. You can just give it whatever specific use case that you need. It's very fast to try this out. You can just use an API and give it your code and tell it to do a thing, and out comes your output. But the negatives are quite high, right? The LLMs are still hallucinating quite a bit. You have to do a lot to constrain that. The failures here are very risky to Uber's business. Uber is the mobile app for the most part. If our app, and we're trying to migrate the mobile app here. So if we put out, buggy code that's causing crashes in production, that can be very expensive to fix. And when we're looking at the amount of code that needs to get reviewed, this gets into the third point that humans are fallible. If you're telling a team, hey, you have 1,000 Java files that we just migrated to Kotlin, and you need to review all 1,000 of these and make sure that there's no hallucinations or any bugs in there. That's going to be a tall order for them to complete successfully. And again, we're talking about millions of lines of code for the Uber Java code. So we thought maybe not quite. So we had this previous approach with our JDK tooling, and we are thinking about LLMs together. What if we combine these? Could we maybe limit some of the downsides that came with using pure LLM to do this, but get some of the speed that's associated with it as well? So again, let's walk through kind of the trade-offs in this case. For the positives, we actually had been doing this in other parts of our organization already. We had been using some other tools like linter autofixes, where you would have a consistent rule that was needed that was deterministic, but the AI was taking the failure mode, reading that, and then generating a recipe to do the fix. And then the platform engineer would review the recipe and say, hey, for all types of issues this solves, this recipe will deterministically fix that. So that was a good start. And this was faster than the humans authoring those rules directly themselves. One of the challenges we foresaw was that if we had hundreds of these rules to write, we didn't know what they were up front. So we have to discover them, and then we have to write them. So if we're getting some of that signal from the LLM and they're working with the platform engineer, that could be much faster. Now, on the downsides, this is still much slower than if I just used the ChatGPT API, but it probably mitigates some of those concerns we had. So we thought that this might be a good way forward. So let's talk through that. So we were trying to figure out how we could start to discover these rules that we needed to write. And we thought, well, we've had our engineers, hundreds of engineers at Uber for several years working on migrating. We have that data. Can we produce a data set from that that will help inform this information? And we started looking at the Git history, and we saw that might be viable. And if you remember the history from the earlier slide, during these years, we did have a dramatic increase in our engineers doing manual migrations. So we started to think about how we could design a system to capture that and create a data set. If you've seen some of our previous talks or read our engineering blog, we have a remote dev environment called DevPods. We ended up building a system that utilizes these as a cluster, and we would start a command that would shard out into our monorepo on n number of DevPods. It would then walk through the Git history looking for all the cases where a migration was happening over a period of time, do the verification and builds and some other things to get that information and make sure it was accurate, and then harvest that back to be collected. And at the end of this, we had several thousand migrations that had been done over about a year and a half, which we thought that's a pretty good start to getting some of the information about what we would need to write these rules. So then what we did is we took two LLMs. We created an author and a critic. We found that can be quite effective when trying to minimize the hallucinations or the downsides of a specific LLM. We had it walk through with a very robust prompt and a agentic framework and start to categorize the type of rules that might be derived from the code that we saw, as well as if these were generalizable across the entire repo, or it was like one specific edge case of that one migration that the tool ran into. And then we built a React application and put a UI in place so that real human reviewers that were experts in the field could go look at these and start to read through the rules and say, yes, this is a generalizable rule. The LLM was correct. We should be doing this specific thing. And in this case, this is about public APIs being explicit types versus implicit. And we said, hey, that's a practice we follow, so we should probably have that as a generalizable rule. And so that made a lot of sense. Now, out of these, we saw about half were probably unacceptable and half were acceptable as the idea. So we could then move forward on how do we create these and have the platform engineer in the driver's seat for this. So let's talk a little bit about the rule generation itself. We built a similar pipeline where we take the prompt, we take the data set, we take the sources of Rektify, our JDK pipeline, and then we work with an LLM to draft a rule, walk through the build and test pipeline, and then it gets reviewed by the engineer, and out comes a new rule that we can commit. And then going forward, we can apply this to our pipeline, and that's great. We have a new language feature that is now supported in all migrations going forward. And when there's a failure from the build or the test, this can now iterate in a loop where the LLM can read the feedback, and it can continue trying and making edits and trying to get a viable rule out of that before it goes to the engineer for review. This can take larger context windows using RAG, where it can pull in contextual information like everything we see on the left, but we can also supply this with additional information as needed so we can get more accurate rules. Here's a quick example of that. There's a public issue being tracked in UTrack around the IntelliJ Java to Kotlin converter missing an abstract modifier in certain cases. We were seeing this specifically with our own dependency injection tool called Motif, which is open sourced. It's like a lightweight version of Dagger. We were saying that if we had these scope interfaces that were annotated, there was no abstract object that was being generated for the scope once it was moved into Kotlin, which was required. And so we used this Rektify rule generator that I mentioned before. We called that, we gave it the prompt that was generated from the previous web dashboard, and we're able to get a lightweight rule to handle this use case using the ASC API that we saw earlier, where this looks for the annotation, and if it finds it and it checks that it's the specific type that it wants, then it can go ahead and it can add the modifier for us. And so this will run after the IntelliJ Java to Kotlin step as one of our processors and fix this type of issue going forward. So with this, we now have the LLM in place. It's helping us generate these rules. We thought we can accelerate this further, and roughly, potentially 3 years of work to get the migrations of the majority of the way there. That still feels like a bit long, so maybe we can figure out some things to help out with that. But for now, I want to walk into a couple of the other bits of the large-scale change process. So specifically, I talked a lot about validation being important. Let's click into that a little bit more. Validation, you might think, could be as easy as, hey, let's just run CI, and if it passes and our unit tests pass, it's good to land, right? That's a great start, but I don't know how your companies are. We invest a lot in code coverage and tests, but we're still not quite comfortable with where we get off of just one layer of quality check. And so, we might see our CI fail and get back into the loop, and that's great, but there's also a risk that it would miss it. And we are talking about Android apps again for this specific migration, and that adds more complexity than if you were dealing with maybe a service. So if you're not an Android engineer, or if you just want a little refresher on this, what we do is we have a build train at Uber. So every week on Mondays, the build is cut, and then we have about a week of testing, runs integration tests and manual testers and beta users internally before we start a rollout and then an aggressive rollout. Now, even when we turn the rollout to 100%, which we do at the end of week 2 and week 3, it's not until near the 4th week of it being in production, or potentially the 6th week from when the code was landed, that we're around 90% updated by all of the users in the public. Because people may not have auto update on, or maybe only on Wi-Fi, or there could be all kinds of reasons. People have different network capabilities around the world. But overall, if there was an issue, it might take a long time for you to be able to resolve that and get it back into the hands of that developer, or of that user. So in this case, with a large application like ours, with so much regional variance, right? Uber has different airport integrations for different airports around the world. There's all kinds of little edge case and little nuances. If our Java to Kotlin migration missed one small issue in one region, it's possible we may not discover that for weeks. Maybe a feature flag was off, or maybe that specific area just had low usage. And then we start to see the errors much, much later, and now we have a lot of cost to trying to address that, fix that forward, do hot fixes. That's just really expensive and slows down the process. And we found that nullability in the interrupt between Java and Kotlin was one of the highest risks here. It's not the only one, but we have been investing here, so I want to talk about it. Just for a little bit of context, we use nullaway, which is a Java compiler plugin with error-prone that enforces nullable annotations and does some smart analyzing of null in Java. And we've done that for a long time. So our code base is highly annotated and highly accurate on the Java side. So you would think, coming into Kotlin, that's great information. Your risk is much lower. And it probably is much lower, but there's still a risk that exists. One common one we found is if you're using a third-party dependency, let's say the Android jar, and it's Java, and it's not properly annotated. And we consume that in our own first-party Java library, foo in this case. We use the pattern non-null by default, which is its own annotation. But in this case, it will be unannotated in our library because Java said, this came in and it didn't have the annotation there, and it was trying to do some nullaway also will do some bytecode analysis and try to decide if something is safe to be nullable. But at this point, we have the unannotated variable that we're passing over into a consuming feature. And if we migrate that consuming feature from Java to Kotlin, now it was annotated essentially as non-null when it was consumed in the feature because it was non-null by default, as I mentioned. So Kotlin and the IntelliJ Java to Kotlin converter will say, cool, this was non-null in Java, now it's non-null in Kotlin. And if that specific variable, even if it was unannotated coming from third party, never had a null in it, that would be fine. However, the problem is that Kotlin enforces nullability at runtime as well. So even if your Java code just by chance never failed because maybe you didn't null check it, but you also didn't use it in a specific way until later on, Kotlin will fail the very first time that gets passed through. So this is an actual case that we've hit several times with the Android platform where something was incorrectly annotated as non-null, it's consumed into Java, it's some weird edge case in WebView or something, and a null gets passed into that, and Kotlin sees that and says, hey, this isn't supposed to happen, I'm going to throw an exception. So we built a tool called Null Patrol, and this is a Java compiler plugin that is designed to enforce a similar level of runtime null validation that Kotlin does, but for Java code. Now what this does is this is plugged into the compilation process, and this modifies specific call sites, and it will add a hook for every one of these to invoke our Null Patrol library and handle that null and say this was annotated as null or non-null, and it was wrong, and I need to do something with that. Now, in our case, we could have said, let's also fail like Kotlin, but then we might have been chasing these crashed ones in integration tests for years with how many there were potentially. So we instead said, OK, when we run into these, we need to log them. We need to emit them up to Hive. Then we need to dedupe all of these, find the originating spot, and then fix them in code. And so that last bit is something we're still working on, the automatic fixer. But the idea of this is we have this all in Hive now. It's all deduped. We can then use some of the other large-scale change tooling that I talked about and we'll keep talking about and apply these fixes automatically in the Java code so that when they're then migrated into Kotlin, they are safe. Here's a little bit of an overview of the internals of what Null Patrol is doing. It's pretty simple if you're familiar with compiler plugins. This has the class that's being invoked from the stage of the Java compiler, which is then looking at parameters being passed and assignments being made. For each one of those, it's adding the hook that we saw earlier, which is sending it to our internal controller, the dispatcher. And then that just uses a service loader to either no-op or to call into Lumber. Lumber is our internal version of Timber, the logging framework that has default support for our own observability pipeline. So it will just emit that through our observability pipeline. So now we can run all of these in our integration tests and have a large volume of the incorrectly annotated ones that we can go through and fix. So let's move on to the next topic in our migrations. I mentioned campaign management is a difficult problem, getting things in the hands of the engineers to review, getting them to review it. Let's talk about this a little bit. We built a system called Shepherd recently, which is our core platform for handling the campaign management. This is a tool that automatically manages the pull requests from a large-scale change. You define a YAML, like you see on the right, that has a specific command line argument and some UUIDs, and it will automatically run that on the set of code that you want to migrate and keep that refreshed, keep that rebased, automatically notify the correct review groups for the different owners around the company if they have a PR to review. Gives metrics so you can track like how long these campaigns are going on for, what's the failure rate, or how long is it taking to merge. It's designed to democratize LSCs, so engineers from around the company can go in and they can utilize this and configure their own individual campaigns for specific migrations. And then I mentioned already, it can automatically refresh and rebase. Here is just a screenshot of the dashboard, but this is designed for the author of the PRs to come in and manage a campaign for their specific migration. In this case, we're showing one of the Java to Kotlin migrations where we're doing this for a specific area, and it's generating a set of PRs that we can see. And these are on different teams to handle, and it shows the state of these. And then when you click into those, there's very specific information that's authored for the PR. It is a bot that is doing this commit. It is giving very specific information on this, giving info on how to refresh this and do the validation. And this has been incredibly helpful, not just in our Java to Kotlin migration, but in the time since we built this and started launching this to customers at the beginning of the year. We've had over 20 campaigns run through this from across the company in different stacks. So we've talked about 3 of the areas, kind of 4. We talked a little bit about problem identification with the rule generation. But this isn't as exciting as I want it to be quite yet. I still feel like 3 years for that migration is a little bit long. So let's talk about what's coming a little bit sooner that we're working on now. Now, going back to the AI hype, if you're following this, you may be more familiar with agents and agentic AI work. If you're not, I'll just give a very quick overview before we talk about how we're applying this. As opposed to a standard interaction with an LLM where you give it a prompt, it does a one-shot, and then you have your output. An agent is more likely to take the prompt and then run multiple LLM calls and use the feedback from each one to then call the next. And out of that, you're able to get a much higher quality result. And Anthropic, the LLM maker, codified MCP, Model Context Protocol, as an emerging protocol that a lot of the different companies are adopting now, which pairs really nicely with the agentic model that I mentioned. I've heard this referred to as giving an LLM hands, but you can take your different tools and you can have them define the MCP protocol or the MCP server that they utilize that, and now all of your different agentic clients can access that tool and use it automatically. So in this case, your agents might be things like Junie that JetBrains is investing in, or Block's Goose, which is a standalone command line tool and desktop app, or Cursor, Codex, Claude Code. There's many of these. A lot of them are adding MCP support. And then on the server side, this could be a local MCP server, like it could be looking at your file system or working with IntelliJ. It has its own MCP or VS Code, using Puppeteer to control your computer, running a shell command. Or you could be hosting remote servers, either in your infrastructure or publicly. Like it can access and look at GitHub and the state of PRs, or access Google Drive, or maybe look at your Figma docs. So it gives the LLM all these capabilities to interact with your environment and create higher quality work. And so we're thinking, how do we use the agentic patterns within the Kotlin migrations? Now, we talked about the LLM hallucinating and that we don't necessarily want the LLM making the direct migrations because that's risky. But we have all of these rules, and right now there's still a lot of manual work in the iteration loops and executing the rules and writing new ones, even if we're handing that to the LLM to write. And so we're thinking, how do we use the agent as the orchestrator who's calling the tools and working on that feedback loop instead of doing the direct edit? And so in this model, we took the previous diagram that you had seen earlier, and we can replace the human potentially with an agent that's talking to an LLM. You could give this to something like JetBrains' new agentic programming framework that they announced. And it can then manage this loop, and it can call the right rules. And if there's a failure, it can read that failure and debug it, and then call the rule generation stack that we used earlier and review that as well. And this gives us these capabilities where we can potentially move at a much faster rate. Again, this is projected because this is in the middle of being built, not built yet. But this seems like the logical conclusion to a lot of these until we get to the LLM being hyper-accurate on its own. And then maybe we can actually visit direct edits. Maybe there's tailing use cases where we could start with editing comments or doing other stuff. But as this industry is moving more quickly and we're seeing higher quality results from the LLMs and we're able to constrain them more, provide more information, we may get to a point where we trust some of the outputs. And we can start to have a foundation that we already utilize with that. And then we can potentially add MCPs to every bit of the stack, right? We have a build-cut MCP. The IntelliJ instance already has MCP support. Uber JDK, we could put MCP at several layers of this stack. Now, this may give direct interaction and better debugging controls and information for this agent to run and be able to help us move more quickly in general. And with this, we could project that a little bit faster. We could probably get to around 2 years to complete this entire migration. Now, everything's not perfect. There's a bit of pain points. It's not all speed ahead. We're still trying to resolve some of this. We talked about the reviewer overload already, that if we have millions of lines of Java code to migrate and you're sending that all to different teams, they're going to get tired and probably stop reviewing your code well. We've also seen issues with our own internal CI infrastructure where if we send a high volume of generated commits at it, we can cause overloads that we need to account for as well, especially when it's competing with a high volume of humans that are writing code at the same time, since we have a lot of engineers. And there's still a lot of the validation gaps that we mentioned. There is, as high code coverage and other things that we have, there's still the risk of things sneaking into production, and we need to figure out how to tighten that down. So we are investing a bit more into those specific areas. We have a project being worked on called Code Inbox, which is to help with improved routing to engineers, as well as to add AI reviewers so that we can start to give them more information and help the reviewers up front. We're looking at PR scheduling and priorities so that we can, instead of having these hundreds of generated PRs go immediately to our merge queue, they can be scheduled for after hours or lower priority or dequeued after a large volume of human written disks went through. And lastly, we also have a big investment going on that we've talked about publicly called Dragon Crawl, which is mobile AI tests, where we're using a test runner who's actually manipulating the application like an end-to-end test and acting as the human writer or the driver or the eater, the different actors in our ecosystem, and they're walking through in a way that's much more resilient than standard end-to-end tests. And so the more we can invest there and start to pull those in to catch these edge cases, that's going to give us higher validation signal as well. We really like Kotlin at Uber. We're making a lot of investments. I mentioned we recently built our first centralized platform team as well. Out in Amsterdam. We'll be adding to that more over time, so we'll be hiring. We will be investing in backend support. We don't have it right now. Right now, most of what we're talking about is Android, but it will give us the fundamentals that we can apply to the backend as well, and we'll be looking at KMP as well. So this is a very, very useful tool in our environment. We really appreciate the community and working with folks and want a lot of collaboration. So if you are interested in that, we have a lot of open source projects. Please go check out our GitHub, find how you can get involved. And with that, I have a minute and a half for a couple of questions. And please step up to the mics if you want to ask anything.